Hello everyone, my name is Eric Tanner and I'll be discussing a white paper titled In-Car Positioning and Navigation Technologies, a Survey, and this is authored by Isaac Skog and Peter Handel. So to give a rough overview of what we'll be discussing in this research topic, we're first going to do an investigation of a few different technologies for positioning and navigation, and we'll look at implementation strategies, the accuracy of each, and the costs associated with that. We'll look into augmentation systems, data processing and analysis, fusing the information from sensors together, and my critique on the paper. So the technologies under review here are the Global Navigation Satellite System, or referred to as GNSS. We'll also look into a plethora of vehicle sensors and the benefits of different sensors. And we'll look into digital road maps and map matching. The authors use 4 criteria for determining the performance of different systems, and they're listed here, with the first being accuracy, and this is the degree of the measurement conforming to a standard or a particular value. The integrity is the second metric looked at, and this is just the trust in the measurement that you're getting. Availability, this is a percentage format, and this is the coverage area for which the system works. And continuity of service, this is just basically the on-time and downtime of the system and probability of having connection to your system. So today's modern navigation systems are comprised of a few components, one being the GPS receiver. You'll have second being map matching, and the third being vehicle sensors, such as accelerometers or gyroscopes. Typical applications are for adaptive cruise control, adaptive light control, and road topology information. This paper refers to the modern navigation system in a car as an advanced driver assistance system. As a navigation system designer for the automotive industry, there are tons of options when it comes to a navigation system solution, but the automotive industry, cost is the main driver for all the systems, and so going out and buying the most advanced, expensive navigation system isn't really the goal here. The goal is to use low-cost components, pairing that with signal processing, filtering the information, trying to reduce the noise from your sensors that are lower cost and may not work as you would expect them to. And then also using multiple sources of data collection so that you can kind of average out the error from maybe relying on one source for the data. So the Global Navigation Satellite System that is referred to in this paper, they don't talk a whole lot about the radar background of what's happening and the details of maybe the radar range equation and how waves propagate through air, and they just cover the basics. So that's all I'm going to do here. But essentially what's happening is you have a satellite that's emitting electromagnetic energy that propagates through the air and is received by a GPS receiver. And so that GPS receiver receives the electromagnetic energy, which contains data, and what they do is the data actually has timestamp in it, and that is how they're able to estimate the distance from the object to the satellite by a electromagnetic wave being timestamped at the time of being transmitted, and then the receiver knowing that known time, calculating the delta, and then determining the distance. They also use multiple satellites for triangulation in GPS systems and navigation systems. And Also, the receiver has knowledge of the satellite positioning, which was key here in being able to determine positioning. At the time this paper was written, there were only two sources for the navigation systems, for satellite-based navigation systems. The third one, the Galileo satellite navigation system, is not mentioned as a currently operating system, but I've researched it and it's operational and functioning. At the time of this paper being written, this was still under development and was not deployed in the field, but it currently is. So we'll start at the top here. The global positioning system, which is a lot of people are familiar with, GPS. This is developed by the United States, and it has good coverage in the mid-latitude ranges. Number two is the Global Satellite Navigation System, and its acronym is often referred to as GLONASS. And this is a Russian-developed navigation system. I'm not going to try to pronounce this, but this is the Russian translation for the GLONASS system. And this system works better at high latitude ranges. And third, this is the more recently developed, it was added in 2013, is Galileo, and this is developed by the European Space Agency. And the unique thing about this satellite navigation constellation is that it is compatible with GPS, which is great, and I think that compatibility across systems is beneficial for everyone. Although satellite-based navigation systems are great, there are some fallbacks to them, which make it the reasoning for not solely relying on these systems for all of your navigation needs. And one of the biggest fallbacks is signal coverage, and especially in an urban environment. As you can see on the picture to the right, you have what's referred to as shadowing, and this is the loss of satellite signal due to buildings, structures. When you're parked in a car garage, you'll have issues getting signal through the cement of the car garage. One of the other things that you'll run into is multipath propagation, and what happens here is a lot of times you'll have reflections of the signal that won't get directly transmitted to you from the satellite. There'll be delayed time versions of the same signal that got reflected off of, say, glass or metal, and they arrive slightly different time to the signal that you're expecting, and you can get instances of what is referred to in the radar world as constructive and destructive interference. Constructive interference is when the signals tend to have like an additive property where the signals add together, or you could have destructive interference where they cancel each other out, further reducing your ability to receive the signal and be able to distinguish the signal from the reflection. So the solution for some of these issues is to not just solely rely on satellite navigation. You want to complement it with sensors and road maps to help kind of break apart the issues from satellite navigation and use other methods to help correct for errors. So the range errors associated with satellite-based navigation systems are put into two categories: common mode errors and non-common mode errors. Common mode errors are correlated between receivers within a local area, and the errors are typically due to delays through the ionosphere and through the troposphere. Non-common mode errors, they're depending on the design of your receiver, the noise in it, and also multipath effects in that local area. On the right here you can see we have a chart here for the standard deviation in meters of the error from common mode versus non-common mode. As you can see, common mode errors tend to create a higher standard deviation than the non-common mode. Your multipath and receiver noise, they don't contribute as much to your overall error, but the common mode end up being a larger contributor and need to be taken into effect in your receiver, and not relying solely on the answers that you get from the satellite. So to compensate for these errors, there are augmentation systems. And what augmentation systems do is they try to compensate for the larger contributors of error, which are the common mode errors. So one of the unique properties of common mode errors is that for a local area, the common mode errors are the same. So the augmentation systems are able to correct for a local area, and then there's a network of augmentation systems that is able to transmit point to point and communicate errors across a larger area. They transmit local error correction to the receivers, and they're referred to as a differential global navigation satellite system, or DGNS. Couple of I'll mention just a few. The picture on the right here has kind of a drawing or partition of the Earth and the different systems for augmentation. You have the Wide Area Augmentation System, which is developed by its coverage for augmentation in North America. The EGNOS, which is the European Geostationary Navigation Overlay Service, that obviously covers Europe. And then Multifunctional Satellite Augmentation System, this is for Japan. And as you can see, there's a couple others on here, like the GAGN-AN is for India, and there's a few others here for Europe. Another method for compensating for errors in a satellite navigation system are integrity monitoring, and specifically the term used is receiver autonomous integrity monitoring. And this is when a satellite-based receiver uses multiple inputs to get a higher accuracy in the estimates that it's receiving. And so for a minimum to do fault detection, you need 5 satellites, and 6 satellites are needed for actually isolating the fault. There's an example used from signals from the GPS, GLONASS, and Galileo constellations, and this was able to, using this integrity monitoring, was able to detect faults of 20 meters with an 80% probability, and with a 90% probability able to isolate those faults. Unfortunately, this integrity monitoring is not effective in dense environments. So in an urban city where you have the multipath issues, it's not going to work as well in this type of an environment. So that's, maybe one of the downsides of using this in your application. Today's vehicles are literally covered in sensors, and they provide information about the vehicle such as attitude, speed, acceleration, and they're oftentimes paired with the satellite-based receiver, and this enables for a complementary pairing to create a more accurate solution. This paper discusses a few different types of sensor technologies, one of the first being the steering encoder. This encoder measures the angle of the steering wheel, which is able to give information to the navigation system to calculate wheel angle. The steering encoder, which is the driving wheel angle, might be slightly different than the axle wheel angle, and so it might not be a one-to-one relationship, so there may need to be some sort of a conversion or scale factor thrown in for this type of a sensor. The odometer, this measures wheel rotation. We have a velocity encoder. This also measures wheel rotation, but it outputs velocity as a result of that. And one of the things noted in this paper is that you can actually determine the direction or heading change in a vehicle by having the velocity encoders on both the right and left side of the vehicle, all four wheels, or just one sensor on the right and left side would also work. But you can determine the direction in which the vehicle is going. The only downside to that is it's not the most accurate heading information because there are errors from the wheel slip, uneven roads. If you have different diameters across your wheels, that might not be the biggest contributor, but it's a contributor if there are different diameters in your wheels. And then the low sample rate of the encoder also contributes to some error. Electronic compasses can sometimes be found in today's vehicles, and they use magnetometers to measure the Earth's magnetic fields and determine direction in reference to true north. The downside that's noted about these compasses is that large metal structures such as bridges and buildings cause errors in the estimates. Also, electrical power lines can cause issues in these estimates. So that's just a note for designing that you might not want to solely rely on this type of a sensor. You have accelerometers that measure the rate of change of velocity with reference to Earth's gravity. A gyroscope, which also measures angular velocity but with reference to Earth's gravity. And today's low-cost sensors are MEMS technology typically, and MEMS is micro-electromechanical systems sensor technology. And the great thing is that these sensors being driven down in cost helps get this type of a sensor put into an automobile. The downside is that you take a performance hit with the lower cost sensor. And so due to this and some of the things we've already discussed, just standalone vehicle sensors are not solely relied on for a navigation solution. And some of the reasoning is that there are biases in some of the estimates, scale factors that are not always one-to-one, non-linearities in that same regard, and sensor noise is a big issue with some of these MEMS technology devices. This paper discusses 4 coordinate systems. The coordinate system used by your navigation solution is very critical in that the sensor data that you're getting needs to get translated to a coordinate. And if you have the wrong coordinate system, you could be in a completely different place than you think you are. So the first system that we're going to talk about is the vehicle coordinate system, and this uses the vehicle as the reference point, and the origin is commonly the center of gravity of the vehicle. The second coordinate system is the Earth-centered inertial system, and this has its origin at the center of gravity of the Earth, and this is also the most popular system used. And then the Earth-centered Earth-fixed is just a slight variant of this, where the system actually rotates with the Earth. And then our fourth is the geodetic coordinate system, and it uses WGS84 as a datum. And I'll be honest, I did not understand what that meant, so I did a little bit of research and figured out first that WGS84 is a standard used in cryptography and satellite navigation, and it's also used in GPS systems. And a datum is just a reference system or an approximation of the Earth's surface against which positional measurements are made for computing locations. So now that we've talked a little bit about the collection of the data and the source of the data, now we need to talk a little bit about the processing of it all. And one of the first steps in processing data is to take the sensor data and translate it to a coordinate system. This is referred to as dead reckoning. Dead reckoning also is combining all vehicle sensors into a position and attitude. And there's also inertial navigation, which is a slightly different variant in that it only combines the inertial sensor data to get vehicle position and attitude. This block diagram here is in the paper, and it is an overview of the inertial navigation system. And it gives a good overall view of how everything is comprised in this type of a system. And over here on the left, you can see within the INS there is an IMU, which is an inertial measurement unit. And in this particular block diagram, there's accelerometers and gyroscopes providing the data. And that data gets fed into the next block, which is an error compensation block. And this tries to remove some of the errors that we talked in previous slides about. And then that gets fed into this other block, which is a computational unit. And this unit contains all of the translation algorithms for sensor data to attitude and positioning information. So inertial navigation systems and dead reckoning algorithms produce errors that are not ideal. Because of all the integration in both of these algorithms, they create a low-pass filter on the data, and there's the good side of that is it reduces the error in the higher frequency areas of the sensors, but it also amplifies the low frequency error. This produces a bias in your estimates, and also the error from this grows without bounds, which is not ideal at all. On the right hand side you can see an RMS plot of horizontal position error over time, and the unit on the y-axis is in meters, and you can just see it rapidly starts growing without bounds. So this is just another example of why not just one system is your sole provider of your positioning, and multiple systems need to work together to create a good navigation solution. So next we'll talk about digital maps. Digital maps is a visual aid for the driver to navigate. If we had just a screen showing up with coordinates, it would be very hard to drive and view these coordinates and try to understand, when to turn right and when to turn left just from looking at these numbers. So the term map matching is taking coordinates and putting them on a digital map for humans to be able to read properly. Another good effect on this is that when you have a digital map matching, you can impose constraints on the navigation system to actually reduce the number of possibilities for places to go. So if you're able to turn right, but there's a dead end to your left, it helps the navigation system realize that maybe turning towards the dead end isn't the correct solution for getting from point A to point B, and so it helps reduce the number of possibilities for the system to calculate. The steps for map matching are to find a set of candidate arcs and then find the likelihood of candidate arcs using the geometrical and topology information. So trying to understand, is it possible for a car to go from point A to point B through this path. And then the final step in all of this map matching is the location of your vehicle. So the overall theme here with this research is that not one system is the right answer for your navigation solution. You need to try to use multiple sources of information, and this is referred to in the paper as information fusion. And essentially this is just taking all the different topics we've discussed so far and pairing everything together to create a more elaborate, sophisticated navigation system. So in doing this, you have two different ways to kind of process the data, and there is a centralized filtering mode and a decentralized filtering mode that we're about to discuss. And these are methods for pulling in the data and processing it for your navigation system. So we'll first talk about the centralized filtering mode. And centralized filtering works where all filter data is fed into one filter to produce a navigation solution. And the benefit to this is that the algorithm has access to the entire data set of sensor data and can produce the most optimal output. The problem with this is that it's computationally complex, and it's typically not feasible to process all of this data at once and in parallel like this. So to mitigate from the extra computations, decentralized filtering modes are used to make the equation a little bit easier to solve. So you have these local filters which are in parallel, and they feed a master filter. The benefit to this is that it's not nearly as complex because the master filter sees less of the overall data set and has less to computate. But the con of this is that because it doesn't have access to all of the data, it typically cannot make the most optimal decision or estimate for the system. So the biggest takeaway from this paper is that there is not one right answer for your navigation solution. It is very application specific, but what is very clear is that you do not want to use a single source of information. A single source of information, as we've seen, has its downfalls and errors associated with it. So what makes the most sense is to combine several sources of information to pick the best attributes from each and create an overall more sophisticated navigation system. And so in conclusion here, I want to critique this paper a little bit. My overall critique of the paper is good. I really like the content of it. There are a few grammatical issues that I saw at the very beginning of reading this, but once I fully digested the paper, I was able to look past some of those because there was some good information here. And I felt like it was a well-rounded overview or update of where current automotive navigation systems are as of 2009. I'm sure there's been a lot of advancements since then, but this was a great way for me, not knowing that much about this area, to get a good introduction. It's not intended to be a deep dive, and I'm completely okay with that. The authors are upfront about that. They say that it is not a detailed description of each one of these, but just a introduction to each area. And so ultimately, I think it would be great to see some extra research from these guys to go with this paper, and maybe particularly a paper on each topic that they discussed in shorter details here, but have more implementation approaches and getting into a lot more of the details and the math behind each one of these data sources and navigation system components. But overall, it was a good read. I enjoyed it. I learned a lot, and I hope that through me presenting some of this data to you, you're able to take away something that you didn't know. And I just want to, in conclusion, thank you all for your time, and talk to you next time.